Okay. Enough words. Let's give some examples here. We'll get to the pictures. A lot more fun. So safety. You like to select reagents that are safe for handling. This particular reagent that I've drawn up here is a diazo transfer reagent. Nucleophilic attack here generates the alkyl or aryl azide. So it's a diazo transfer reagent. What I am pointing out, though, is the stability of the reagent itself. So if you have just the free base, it's highly sensitive to impact and friction. You look at this molecule and think, yeah, it would break here, you liberate SO2, you liberate hydroxylic acid, you are dealing with gases, and you want to be able to understand and control the generation of such compounds. So the free base is not a good thing to deal with. The hydrochloride salt exploded during synthesis. Thank you, no. The perchlorate salt is even more hazardous than the free base. No thanks. The fluoroborate salt is safer, but as you would expect, more expensive. How about just the simple sulfuric acid salt? Simple. It's easy to do is easy to say. I still would be concerned about making this compound and about using it. And in fact, perhaps the best thing to do in terms of safety is to outsource dealing with a compound like this to someone like AMPAC, people who handle high energetic chemistry. So outsource your problems. Sometimes that's the best approach. Okay, so batch operations, safe handling for, again, a compound that generates a gas. And this is a courteous rearrangement. You start out with the carboxylic acid, generate the mixed anhydride with diphenylphosphoryl azide, and you generate the anhydride, azide attacks, you get the acyl azide, which then with heat rearranges. Then, the isocyanate gets trapped with benzyl alcohol to give the protected amine. Okay, classic name reaction chemistry. And the key point here is controlling the emission of the gas. So how to do this? With a dose-controlled addition of the key reagent itself. So all of this makes sense. And it was an addition at a moderate temperature, about 85 degrees, to control the liberation of the key byproduct here, the nitrogen, dinitrogen. So this then is one way to do it, say scale up in a batch-wise mode. Alternatively, here's another courteous rearrangement that was done in a continuous fashion. Now, this is a kind of a busy slide, so I'm going to walk you folks through this real quickly here. It starts out with the bis-acyl azide. This is in hydrochloric acid, aqueous hydrochloric acid. Gets pumped into a microreactor. Simultaneously delivered into the microreactor is a solution of sodium nitrite, and with the HCl that's around, this then generates nitrous acid, and then toluene as the other carrier. They get mixed in the microreactor, come out, and so then you have two phases. You have an aqueous phase and an organic phase. The aqueous phase is just waste. The organic phase is the alkyl azide. This then is heated to generate the bis-isocyanate, and then this is automatically quenched into aqueous HCl and crystallized to give the bis-hydrochloride salt. So that's how all of this fits together. Why they did this, though, is because the bis-azide, acyl azide, started decomposing below room temperature. And it was quite exothermic decomposition. So in order to make sure that they had no accumulation of the acyl azide, they ran it in a continuous process, generating it and then converting it over to the bis-isocyanate and then quenching it. So by doing it continuously, they had only very small amounts of any of the highly reactive material present at any time. So that's the thrust behind this. Now, this again was done by Aldrich. Aldrich used their glass microreactor in order to get the job done. They were generating this material for their catalog. So it works out really well. And I want to point out one aspect here which I thought was really wonderful, elegant in its simplicity. They had an automatic phase separator here. So when we think about continuous flow chemistry, we think about continuous reactions usually. But you can have continuous separations, continuous quench, continuous separations, continuous crystallizations, continuous evaporation of byproducts. All of these things can work out. It's not just the continuous reactions themselves. So in this particular case, the aqueous phase was just the sodium chloride, basically. So it's not needed, and it was automatically separated. And what the folks at Aldrich did is they just ran it into a SEP funnel, your basic Aldrich SEP funnel. And they knew the rate at which all the inputs were coming into the SEP funnel. And then they used a pump to drain off from the top layer and process this on through heating to get to the bis-isocyanate. So the pump withdrew the top layer. Inputs were coming into the SEP funnel, and then they just adjusted the stopcock in order to drain material, the aqueous phase, out the bottom, and hence keep the level of what was in here relatively constant. So elegance and simplicity, yes, I really like this. However, if you take a step back from this for a minute, you realize not only is this cool, but this is basically what a continuous separator does on a large scale anyway. So it's a nice application of getting things done. So continuous flow reactors can also help to contain volatile components of your reaction mixture. The example that I've put up here is from some people at Hoffmann La Roche in Switzerland in connection with Professor Britton. And basically, the reaction is an inverse electron demand Diels-Alder reaction. You heat this at about 230 degrees. Cyclopentene undergoes the formation of this tricycle with elimination of water and re-aromatization. The pyridine results. Now, this is a pretty sweet yield to get to where you want to go. An unusual type of material. What they were actually doing was generating this for a med-chem scaffold for diversity screening. So why did they go and take a look at continuous operations to do this? Because of the temperature that was needed. And they did quite a bit of screening. 230 degrees, you are well above the boiling point of the one component. Continuous operations wasn't their first choice. Their first choice turned out to be putting it into little vials, crimped, and they would do microwave reactions. But unfortunately, when they did that, the cyclopentene leaked out. So their nice choice then was to go into continuous operations because with continuous flow, you can handle the pressure. So a nice example of practical approach to get to where you want to go. Now, with continuous operations, I've spoken with a number of you about that briefly. It's one of my favorites, certainly. If you look at organic process research and development and critically look at the papers that are in there for continuous operations, well over half of them, in well over half of them, the continuous flow reactions were developed from safety. And one additional point to add on to this. If you go to your chemical engineering counterpart and say, hi, I have an experiment here. I think this would work really well in continuous flow. You're probably going to get real rapid buy-in from these people because your ChemE is going to go, fantastic. I've read about all this stuff in school for years. Let's do it. So it's something here that has great potential, and I strongly encourage you to consider it when it's appropriate. Not everything fits into the shoebox called continuous operations, but a number of things work much better for scale-up. So speaking of scale-up, this is the one that I mentioned earlier to some of you folks, the Ritter reaction that DSM has done. Diacetone alcohol plus acrylonitrile to generate a monomer. Now, they did this basically for economic reasons, safety and economics, to get the job done. This is a very economic reaction. They can control this. They can contain some pretty reactive components here under a temperature that causes you some concern. With rapid processing, they can minimize decomposition of the goods. But look at this. The waste decreased by 15%. The yield went up by 15%. And they could make 40 tons a day using this microreactor. Now, it's a falling film reactor, which is something that the industry is well familiar with for highly corrosive materials. Toxic acid, for instance, has been made through sulfonation of toluene using a falling film type of reactor. So again, if you have a continuous process that you think might help you, you're probably going to find that there are considerable promises there that can help you. Workup considerations. You've generated the goods. Fine. Your HPLC says it's there. How do you put it into a bottle? Okay, the workup is the next most critical part. We want to quench the reagents in order to prevent further reaction, because usually the reagents are there in excess. Not always, but usually. And we want to quench it at a point in the processing where we have the highest concentration of product and not degrade the goods. One of the things that we often overlook as chemists is whether or not a reaction is an equilibrium reaction. Equilibria need to be quenched positively, actively. Otherwise, with the extended operations that you expect for scale-up, you are very likely to see the equilibrium shift away from what you want for the product. Now, this is true for particularly biocatalytic processes. Many enzymatic processes are equilibria. We'd like to use extractions to simplify the workups. We'd like to use adsorbents to make things easier, whether they're charcoal, sea light, or something in between derivatized silica gels. But that can be very time effective, especially in an early development stage. Column chromatography may also be very practical, especially early on. Now, how can you, I've spoken with some people, other CROs, and they've said, yeah, we do column. Why not? It's quick. We know how to handle it. We're familiar with it. The first question we're going to ask people is, can you separate it by TLC? If you can separate it by TLC, then we can probably find a pretty good way to do it by chromatography. On the other hand, there are some pretty sophisticated capabilities out there that for separations, such as SFC, supercritical fluid chromatography, in order to get things separated. And it turns out that many of these There are many examples where SFC has been used very economically, and it does work. So fit for purpose is how we need to approach most of the things that we deal with. Yes, it's very nice to optimize things to the nth degree and make sure that everything works well, but we don't have enough time to do that, and things have to be fit for the scale, for the phase of the operation. And I wanted to bring this example out here to kind of drive that home. The benzene thiol here was generated in methylbutyl ether, and they wanted to get this into acetonitrile for the next reaction. So one of the things that many medicinal chemists would do is to say, well, you just put it on a rotovap and rotovap it to dryness. And you can't do that for the most cases on a large scale. Now sometimes you can strip things down to a very low level of a solvent, but it's time consuming and it's difficult to get down to below 5% of methylene chloride, for instance. So what these folks did was to have their MTBE solution, strip it to the minimum agitation volume, add in the solvent, higher boiling solvent, strip it again, hence chasing out the solvent that they don't want around in order to get it into the solvent that they do. Second step then is the formation of the bis-thioether, aryl ether. And so this is done in the absence of palladium. I mean, hello, this is almost not American, right? You're doing a coupling here without palladium here. But it's pretty nice to be able to do this, and it makes sense. You have an electron poor substrate. You're putting in a relatively strong base, tetramethylguanidine. Mild conditions, polar solvent, and it works. So it works quite nicely. Then the product that gets generated is a benzaldehyde. Of course, this is going to be prone to air oxidation. So how to deal with it? These folks then reacted it with bisulfite in order to generate this bisulfite adduct. And that was crystalline. So this is how everything was driven for practical natures. Now, what I wanted to point out here in particular is that they had a 48-hour reaction time. Now, most CROs, when they see a 48-hour reaction time, are going to say, oh yeah? Was this done over the weekend? Do I need to do this? But if it turns out that 48 hours is really what you need in order to make the material for your particular phase of study, early on, you're going to be happy to do this. So everything works out to have a lot of dependency on the time and the phase of your operations. Quenching, again, active quenching is really needed for equilibria. And I've tried to underscore this here with the arrow. So ring closing metathesis, it was necessary to actively expel the ethylene that is produced. But what happened is that this olefin, in the presence of the excess Havadas catalyst, can ring open and go back. And when it goes back, then in the presence of the catalyst, it can react again to form dimers and trimers. Now, on a large scale, this was a problem. Small scale, no big deal. You just take your reaction mixture and you pour it on top of a column, right? And you filter it all down. On a large scale, though, that transfer time and that filtration time took a long time. And when Behringer Ingelheim folks did this the first time around, they got a very disappointing yield of the macrocycle. So what they reasoned that they had to do was to actively quench it. And the one that they talked about in the papers is the 2-thionicotinic acid. The imidazole was mentioned in their patents. They have to actively quench the reaction by coordinating to the ruthenium and stop the reaction from going back to the left. And again, this was the processing to convert the sulfonate ester over to the ring-closed sulfonate ester. I also want to point out that in order to get this reaction to go, they had to consider the impurities, because they're dealing with a very low level of catalyst, reagent. So if you're have a low level of reagent, you have to be more concerned about the impurities that could potentially complex with it and form problems. And so they went through extractions to pull out secondary amines, the hydroxyproline derivative that came from making the amide, unacylated hydroxyproline, the secondary amine from morpholine. Now, how the morpholine got in there is an unanswered question. It was an impurity in the toluene, and why it was there, this is just what is. HOBT also inhibited the reaction itself. HOBT was a byproduct from using TBTU for the coupling to make the acylated proline derivative. Not something we would like to be using routinely on a large scale, TBTU or HBTU, things like this. But this is what they did for this particular phase of their operations. And they optimized this very nicely further down the road and did talk about it. So active quenching can be extremely important.